Welcome to third lectures on terpenes and terpenoids. In this lecture, we are going to discuss the chemistry of geraniol. First of all, we will see the occurrence as well as uses of geraniol. We will discuss the structure determinations as well as synthesis of geraniol in very detail. Geraniol is a trans isomer and nerol is a cis isomer. So we will discuss the cis trans isomerism between these two molecules. Geraniol is a typical allylic alcohol containing two double bonds, and therefore its oxidation reactions are very interesting. We'll discuss few oxidation reactions of geraniol. At the end, we will discuss the 1H as well as C13 NMR data of geraniol. First of all, let us see from where geraniol we get. The major source of the geraniol is rose. Another sources are palm rose oil as well as citronelle oil. So when we extract geraniol from these sources, generally it appears like yellow liquid, but the pure form of the geraniol is a colorless liquid. Geraniol is having a very pleasant smell of rose, and therefore it is used in perfume industry. It is used in the manufactures of lotions, creams, detergents, shave lotions, soaps, as well as various bathing products. Geraniol is also having some medicinal properties. It shows it is an antibacterial, it is antiseptic, and it can also act as an anti-inflammatory product. Now let us discuss the structure of geraniol molecule on the basis of chemical methods of analysis. In the earlier days, chemists were not having sophisticated physical methods available, and therefore they were relying on the chemical methods of analysis. In these chemical methods of analysis, the first step is the isolations of geraniol in very pure form from rose oil. After the isolation, it is subjected to various chemical reactions. From these chemical reactions, we have to reach to the structures of the geraniol molecule. In this investigation, the first step is the estimations of carbon and hydrogens. From estimations of carbon and hydrogen, chemists were reaching to the empirical formula of geraniol, and from empirical formula of the geraniol, they were getting the molecular formula of the geraniol, and it was found to be C10H18O. The molecular formula of the geraniol is a very useful information in structure of geraniol molecule. Here it contains carbon, hydrogen and oxygen. It means geraniol is a terpenoid molecule. It contains 10 number of carbon atoms. It means that there are two isoprene units, and because of this presence of two isoprene unit, it belongs to a class of monoterpenite. Again, according to the special isoprene rule, we can assume that these two isoprene units may be joined through head to tail linkage. So just by say 10 number of carbon atoms, we get a rough idea about the structure of geraniol molecule. Another useful informations we get about the structure of geraniol molecule from molecular formula is the degree of unsaturations or double bond equivalence. Now for a molecule CXH5OZ, the double bond equivalence is calculated by formula x plus 1 minus y by 2. So if we keep the values of 10 and 18 here, we get the degree of unsaturation is equal to 2. Now what is the meaning of this degree of unsaturation is equal to 2? It means that geraniol may contain the two double bond, it may contain the two rings, or it may be the combinations of one double bond as well as one ring. So in the subsequent investigations, we have to find out the nature of these unsaturations. Therefore, the next experiment is the hydrogenation experiment to find out these unsaturations. When geraniol is subjected to hydrogenations, it forms C10H22O. It is called as tetrahydrogeraniol. So chemists were isolating this compound in pure form. They were again subjecting to the element analysis, and they were finding the molecular formula as C10H22O. Now after this experiment, if you do some chemical arithmetic, if you subtract the molecular formula of geraniol from the molecular formula of the hydrogenation product here, we see that the two molecules of hydrogens are consumed by geraniol. And since it has consumed two molecules of hydrogen, we say that we assume that geraniol molecule contains two double bonds. Similar experiment is a bromination. Here two molecules of bromine are consumed by geraniol. So on the basis of hydrogenation experiment as well as bromination experiment, we conclude that geraniol molecule contain two double bonds. So out of this two unsaturation, this two unsaturation is corresponding to two double bonds here. Now let us switch over to the analysis of oxygen. What is the nature of this oxygen? And for this, a very simple experiment was performed. Geraniol was subjected to oxidation, and the product form is C10H16O. This C10H16O was found to be an aldehyde, and aldehyde formation indicates that the starting material, that's a geraniol, must be an alcohol. The more investigations about this oxidation product revealed that it is a citral molecule, and citral structure we have already discussed in lecture number 2. So on the basis of very simple oxidation experiment, we reach to the structure of geraniol molecule. Citral is a alpha beta unsaturated aldehyde, and therefore geraniol molecule must be an allylic alcohol. So we reach quickly to the structure of geraniol only because of the oxidation experiment. So in this way, just by elemental analysis, hydrogenation, bromination and oxidation experiment varies to the structure of geraniol molecule. Similarly, we have seen in lecture number 2 that citral on reductions gives geraniol. So again we get back geraniol. So this is a very short kind of investigations about the structure of geraniol because we have already know about the structure of citral. Now after structure determination, let us see how this geraniol is synthesized in the lab. There are various methods, some of them are very interesting. Citral on reductions with sodium amalgam gives geraniol, and some small quantity of nerol is also obtained. So in the incoming slides, we will talk more about this geraniol as well as nerol. At that time, we will write the structure here. So this is one method of obtaining the geraniol. Simple reductions of citral gives us geraniol. Another method is Another method of synthesis of geraniol starts from linalool molecule. Linalool is a monoterpenoid. It's a allylic tertiary alcohol. Under acidic condition, it undergoes allylic rearrangement and we get a geraniol molecule. Here the carbocation chemistry is involved here, and similar kind of carbocation chemistry will require in understanding the biosynthesis of this terpenoid molecule. This is a laboratory synthesis of geraniol from linalool. The third synthesis is involving co-rearrangement, 3,3 co-rearrangement. This is a diene here, isolated diene here, and this isolated diene undergo 3,3 co-rearrangement, 3,3 sigma tropic rearrangement, and we get a geraniol molecule. Another synthesis of geraniol involves ethyl acetoacetate chemistry, methyl magnesium bromide and allyl bromide. It's a very interesting synthesis. We have to assemble total 10 number of carbon atoms. 5 number of carbon atoms are coming from allyl bromide here. 4 number of carbon atoms are coming from ethyl acetoacetate. 1 is coming from methyl magnesium bromide. So the synthesis starts from here reactions of ethyl acetoacetate with LDA, lithium diisopropylamide. It generates enolate anion. So this enolate anion is alkylated using this allyl bromide, and we get here vinyl allyl type of the ether. Vinyl allyl type of the ether is a Claisen substrate. When it is heated, it undergo 3,3 sigma tropic rearrangement, and we get a rearranged product. So in this way, we get a alkylation product here, but it's a rearranged product here. To some extent, rearrangement is realized here. Now in this substrate, we do not require this OET moiety. We require this ester. We have to transform this ester into corresponding alcohol, and for that we have to perform its reduction. So if you try to reduce it, this carbonyl group will interfere, and therefore the protections of this carbonyl group is achieved with ethylene glycol. We get a cyclic ketal. And now it's a ether. Ether is inert for lithium aluminum hydride reductions. So we get a reductions of ester group to alcohol, and then under acidic conditions, then this OH group is protected here in the form of acetate, and then this cyclic ketal is deprotected under mild acidic conditions. We get a ketone. So in this way, we reach to the 9 number of carbon atoms. Our requirement is 10 number of carbon atoms for geraniol. This is a 5 number, and this is the 4 number of carbon atoms. 1, 2, 3 and 4 is coming from ethyl acetoacetate. So we are very close to the target molecule now, and for that we have to utilize Grignard reaction here. Its reactions with the methyl magnesium bromide gives us 10 number of carbon atom. It's a tertiary alcohol, and tertiary alcohol undergo dehydration reactions using acetic anhydride, and we get here again diene. This diene looks like a cope substrate, so when it is heated, it undergo 3,3 sigma tropic rearrangement, and we get this alkene. We get this product, and this on hydrolysis deprotection occurs here, and we get OH here. So this molecule is geraniol molecule, and we can rewrite is in this format. So in this way, we reach to the synthesis of geraniol molecule using allyl bromides providing 5 number of carbon atoms, ethyl acetate provide 4 number of carbon atoms, and methyl magnesium bromide provides 1 number of carbon atom. Various concepts are involved here. This enolate chemistry is involved, sigmatropic reactions are involved, protection and deprotection strategies is involved. Here is also the protection and deprotection to some extent. It is protected as alcohol is protected, and later on the alcohol is deprotected here. So this synthesis is very interesting as far as the concepts are concerned. Now let us see the cis-trans isomerism between the geraniol as well as a nerol molecule. We have seen that when citral molecule is reduced, it gives a geraniol, and apart from geraniol, we also get a small quantity of another molecule, that's a nerol molecule. Now this geraniol and nerol molecule is having the same molecular formula. They are having the same connectivity, but these two structures are different only because of the double bond here. This double bond is to some extent a trans, and this is a cis here. So this geraniol is a trans isomer and nerol is a cis isomer. And in the earlier days, these two were differentiated on the basis of chemical methods again. It is found that geraniol on reactions with H2SO4 forms alpha terphenol. Nerol also reacts with H2SO4, it also forms an alpha terphenol. But nerol as a cis form, it reacts 9 times faster than that of the geraniol, and obviously the rate is obvious because this allylic alcohol is in very close proximity with this trisubstrate double bond, whereas this allylic carbon atom is far away from this trisubstrate double bond. So we will see the mechanism of these reactions, and from this mechanism of reactions again we will understand why the rates of nerol is 9 times faster than that of the geraniol. So this is a star carbon atom, it is very close to it. This is again the star carbon atom. Here we are interested in this cyclization, it is far away. So in the mechanism, first of all, geraniol as well as nerol, both of them are protonated. Protonated OH is a very good leaving group, we get a carbocation. And this carbocation is trapped by this trisubstrate double bond and we get a cyclization here. Now this cyclization process is very slow because these are away from each other, whereas this is very close and therefore it's a fast and we get a tertiary carbocation. Tertiary carbocation is trapped by water molecule and subsequently we get the alpha terphenol. So in this way we have seen that geraniol and nerol, these are the geometric isomers, and nerol undergo cyclization 9 times faster than that of the geraniol. Now let us take another transformations of nerol. Nerol is an isomer of geraniol. Nerol on acidic conditions form alpha terphenol, we have already seen. And apart from this alpha terphenol, it also forms small quantities of limonene as well as alpha pinene. It's a laboratory synthesis. It's a laboratory reactions, and this similar kind of the reactions are done by the nature, but instead of oxygen there is a pyrophosphate, and we will come across the biosynthesis of alpha terphenol, limonene and alpha pinene. So the mechanism of this reaction is very much analogous to the biosynthesis of all these molecules. So here we will see how these two are formed. We have already seen how alpha terphenol is formed from nerol. Nerol is protonated, we get a carbocation. Carbocation is trapped, we get a tertiary carbocation, and it reacts with a nucleophile, we get alpha terphenol. Now this carbocation, tertiary carbocation, is having various options. The first option is that it can remove the proton from this carbon atom, and it removes the proton, we get the limonene molecule, and limonene is present in sweet lemon. Alternatively, this carbocation can be trapped by internal nucleophile like a double bond, and we get a bicyclic structure, and here removal of proton can occur and we will get a alpha pinene. Similarly, from this intermediate we can get a beta pinene here, but it is not shown in this slide. So this mechanism of conversion of nerol to alpha terphenol, limonene and alpha pinene will be useful in understanding the biosynthesis of the terpenates, and therefore it is necessary that one must learn it very well. Now this geraniol is a allylic alcohol containing the two double bond, and it undergo very interesting oxidation reactions. The first one is a specific allylic oxidation. For allylic oxidation, MnO2 is a preferred reagent. Here allylic alcohol undergo oxidations, we get alpha beta unsaturated, that's a citral molecule we get. Similarly, the carbon-carbon bond cleavage, that's a oxidative degradation of geraniol, can be accomplished using transition metal like KMnO4, or it can be achieved by ozonolysis. Now, depending upon the workup in ozonolysis, if you do the reductive workup with dimethyl sulfide, then glycol is formed. But if you do the same thing in KMnO4, then Oxalic acid is one of the product form. Because of this isopropyridine group, we get acetone in both the cases. Here is a levulinic acid is formed. Here is a levulaldehyde. Another reaction is a sharpless asymmetric epoxidation of allylic alcohol. That's a geraniol. Here we get again two enantiomers, and one is major over the another because of the presence of plus diethyl tartarate. Now the last slide is related to the NMR data of geraniol molecule. If you record the NMR of geraniol, we get how many signals? 1, 2, 3, 4, 5, 6, 7, 8 and 9. 9 signals are likely to occur, but here 1, 2, 3, 4, 5, 6 is obtained because these two are getting overlapped here. Now these two methyl groups, in fact, they are different, but they are appearing under the same environment, almost close environment. They are not separable, and here they are appearing at 1.67. Therefore the number of peaks appears to be less in this case. We are having olefinic protons here, and here is also the olefinic proton. It is around 5.40. It's a more deshielded than this olefinic proton because of the oxygen inductive effect. 4.13 is this a very distinct, we'll get a doublet here. This is this 1.60. This is again appearing as a singlet, and these two carbon atoms will appear as a multiplet. This is olefinic protons. Similarly, in the C13 NMR, we will have CS2 attached to the OH 59.2. Then these two olefinic carbon atoms and these two olefinic carbon atom 139, 131, 124, 123. This is a olefinic region. 59 is a carbon atom connected to the OH, and remaining are the CS2, CS2, and these two uh, methyl groups as well as methylene groups will be here. So it's a very interesting NMR of geraniol molecule. So in this way, we have reached to the, we have discussed the chemistry of geraniol, we have discussed the NMR, we have discussed oxidation reactions, we have seen the conversions of nerol into various terpenoid molecules, then the how nerol reacts 9 times faster than that of the geraniol, and we have seen the interesting synthesis of geraniol, and we have also studied the structure determination of citral. So in this way, we have learned the geraniol chemistry. Now it's time to think of the examinations. What are the probable, what are the variety of the problems likely to be asked in the examination? uh, One can ask, predict the products of following reactions. Students will be asked to write the products of reactions of geraniol with bromine, hydrogen, then CrO3 oxidation, acetic anhydride, and diluted sugar. So we have seen it contains 2 molecules of bromine, 2 molecules of hydrogen. It gives a citral, monoacetate is formed, and here it forms a alpha terphenol. So this is a very again interesting revision kind of the exercise. The next problem is on we have to justify it why this happens, and we have to show the structure of nerol. Nerol is a cis isomer, and therefore it undergoes 9 times faster. It's a carbocation chemistry is involved, so one must write the mechanism of these reactions very well. And the last slide is about the mechanism of these reactions. Geraniol transformation into alpha terpenol. Nerol is converted into alpha terpenol. Linalool is converted into geraniol. So these mechanisms students should practice because it will be useful in understanding the biosynthesis of terpenes. So this is all about the geraniol chemistry, and in this way we have completed 2 molecules now. In the fourth lecture, we will discuss about the menthol. So thank you very much for watching the video.